Intelligent Plant's alarm analysis, part of the Gestalt suite, opens on the overview page. This displays the main key performance indicators, KPIs, defined by the Engineering Equipment and Material Users Association, EMUA 191 Rev 3 guidelines, and the International Society of Automation, ISA 1802 standard. Similar information is also available from IEC 62682 and BSEN 62682. These KPIs are intended for use by everyone involved in the alarm management process, as defined in the site's alarm philosophy. Typically, this would mean the site manager, production supervisor, process operator, process engineer, and control and instrument engineer. An instrument technician and/or DCS technician may also be involved. The KPIs can be considered as a benchmark to allow a site's performance to be compared to the standards and to other sites within the company's organisation. The first thing to do is select the time period whose performance we wish to examine. The most effective period is a month, so we have a way where a month can easily be chosen. If we need to look at very specific dates, there is a traditional date and time picker. We also have an overview bar, which allows us to slide along and choose areas of particular interest, so we can see where there were high or low alarm rates. All the controls are coordinated, so we can see that the period we have chosen is from the 1st of September to the 2nd of October. So, for the period we have chosen, the KPIs are displayed. In the example shown here, there is every possible KPI, but for an actual site, we would have a small selection of these. Average number of alarms per 10 minutes, per hour, and per day are virtually the same statistic, so typically we would only choose one of them. These KPIs are based upon an ability of the operator and the time necessary to detect an alarm, navigate within the control system to the relevant data, analyse the situation, determine and perform proper corrective action, and confirm that the action taken has been effective. Studies have shown that this takes about 5 minutes, and as the operator has other tasks to perform, this is why one alarm in 10 minutes is the target we should be aiming for. Each KPI is configurable, and the thresholds and icons that are displayed can be set to values appropriate for the site being benchmarked. The default icons are acceptable, manageable, over-demanding, and unacceptable, and these are taken from EMUA 191 Rev 3, as we felt these categories were more useful and informative than the predictive, robust, stable, reactive, and overloaded categories that were defined in earlier versions. For this KPI, we can see that less than 1 is green, less than 2 is yellow, less than 10 is orange, and by default, greater than 10 is red. This scaling schema is again taken from EMUA 191 and indicates performance more accurately than a linear scale. Under the KPIs, a simple display of alarms over time is shown. The timescale can be based on days or on hours. This lets us see how performance compares to our target over time. So what we can see is on the 4th of September at 4 o'clock, there were 282 alarms, and this was the day with the highest number of alarms in an hour in this month. The next chart shows us at what time of day the alarms were occurring. We can see that between 2 and 3 o'clock in the afternoon, the average number of alarms over the month per operator per 10 minutes was 1.2. This chart can highlight times when alarms are generated by ongoing operations or by maintenance. The number for between 11 and 12 is often very low, as this is usually lunchtime, and the alarms are likely to be the underlying rate generated by the process itself. Next, we have scatter charts representing the overall performance of the alarm system. The first pair were introduced in EMUA 191 Rev 3 and were intended to highlight different performance levels in steady and upset state. The previously mentioned 1 alarm per 10 minutes is the acceptable rate for the steady state, that is, the normal operating mode of the plant. It is accepted that there will be occasional upsets when the alarm rate will be increased, and it is deemed acceptable for there to be 10 alarms per 10 minutes for these short periods. The states are separated because different actions are required to rectify non-compliance in each case. The steady state can be improved by addressing and correcting bad actors, while the upset state generally requires modifications to logic so that alarms are dynamically suppressed when their meaning is no longer useful. A low-pressure alarm on the discharge of a pump may be useful when the pump is running, but when it stops, we expect the pressure to go low. Therefore, it may be appropriate to suppress the alarm in this situation. For each chart, the small dots represent a day in the period selected, and the single large dot is the average of these. The steady state chart plots the percentage of time greater than 1 alarm per 10 minutes against the average alarm rate per 10 minutes, and the upset state chart plots the percentage of time greater than 10 alarms per 10 minutes against the maximum alarm rate per 10 minutes. In this case, it is clear from the spread that performance is quite variable, ranging from acceptable to unacceptable in both charts. Next are the original IMUA scatter charts. In the config screen, it is possible to disable either of the two chart types and only use those considered most appropriate. Although both sets are displaying the same data, it can be seen that performance tends to look better in the older charts. Next, we have an overview radar chart, again introduced in IMUA 191 Rev 3. This plots average alarm rate against percentage time above 1 alarm per 10 minutes, which is the steady state, against percentage time above 10 alarms per 10 minutes, which is the upset state. The thresholds for the colour changes are the same as in the charts above. So, fairly obviously, we want our triangle to be as close to the central green area as possible. This chart is a very succinct overview of performance and could almost be used on its own as a benchmark for managers to use. Beside this, we have a pie chart showing the overall priority distribution. Most sites have 3 priorities: emergency, high and low, or critical, warning and advisory, for example, and the distribution should be 5, 15 and 80%. We only want 5% of alarms to be emergency or critical priority, so that these alarms, the most important ones, stand out. As it happens, for this site, there are only 2 priorities, and most alarms are of the alert type. And finally, on the overview page, we have a chart developed by Intelligent Plant, and which is not defined in any of the standards. It is a histogram type chart which shows the counts of alarms in each of the 10 minutes over the period selected. The intent of this is to show performance without any biases introduced by averaging. As there are 144 10 minutes in a day, one 10-minute period with 144 alarms will by itself raise the average for the day by 1. In a modern integrated system with control, shutdown and fire and gas functionality, it is quite possible for this to occur. We can see that for this system there were 2024 10 minutes with no alarms, and that in fact no alarms is the most likely number of alarms for there to be. The green columns show acceptable performance, the yellow manageable, the orange over-demanding, and the red is unacceptable. We can see that the performance is acceptable for 66% of the time, but is unacceptable for nearly 6%, and is in upset for 3.9%. And since our upset target is less than 1%, this is significantly higher than desired. All 10 minutes with greater than 10 alarms go into the blue column, and we can see this happened 169 times. We can also view this on an hourly basis. Again, we see that the system is mostly in the green, and that the most likely number of alarms for there to be in an hour is 3. Again, we get some summarised statistics which are similar, although not the same, as those for 10 minutes. This highlights that we need to be consistent with which KPIs we report, as a figure calculated over 10 minutes will not be the same as one calculated over an hour. So, that is the overview page, which would be used by the managers and key stakeholders to monitor system performance. There is a tab with some supplementary information. There are plots of the main KPIs, average alarm rate, peak alarm rate, and percentage time in upset over time. We can see that there must have been some kind of significant event on the 9th of September, as there is a peak in each chart on this day. At the bottom there is a plot illustrating when and for how long the system is in flood. The count of alarms per 10 minutes is shown, and the barcode indicates when this corresponds to flood. There is a vertical green line for each 10 minutes that are considered to be in flood. We then extract some KPIs from this, so we can see that the highest 10-minute period was 128. The highest flood occurred on the 4th of September at 1540. The number of floods was 124, and the length and time of the longest flood, in this case, was 2 hours. Clearly, this would have been a trying time for the operator, and it is possible that many alarms were missed or not properly acted upon, with possible safety implications. The definitions of flood and upset are slightly different. Upset is greater than 10 alarms in 10 minutes. A flood begins when there are greater than 10 alarms per 10 minutes, but does not clear until there is less than 5. This is why the time in flood figure here is 6%, which is different from the 3% upset we saw previously. The definitions are from different standards. Both are calculated so that each user can use the one he desires. Lastly, in the overview, there is a History tab, where we can see how the KPIs are changing over time. This would be useful if an active alarm reduction program was in place, and we could see how effective the improvements are being. There is no data for these 3 months, so if we change the month to December, then we can see what the trend is over time. In summary, the overview tells us if we have a problem or not. Now we'll move to the Bad Actor tabs to see where the problem is. This tab is for the alarm champion, the instrument or DCS tech, and the operator to look at. We would not expect this to normally be examined by management. Firstly, we can see the overall top 20. What we usually find is that there are few alarms that are effectively broken and coming in and out of alarm far too often. Here, the worst alarm has happened 600 times, and each of this 600 was not useful to the operator. So, 6.4% of all alarms that occurred were 81 LAHH 1113. Fixing this one alarm would straight away remove 6% of the alarms that happened. We have a list of the top 20. We then chart them so there is a graphical representation, and we accumulate them with the orange line so that we can see that altogether they are responsible for nearly 40% of all alarms. Fixing only these 20 would remove 40% of the alarms. The effect of this can be seen in the next chart, which is alarms over time as before, but now we have changed the bad actors to be blue, with the green being the alarms that are left with the bad actors removed. We use the barcode display again to show when the bad actors are occurring and when they are standing. Each vertical line shows when the alarm was active, so we can see where the alarm is chattering and where it is standing. We can also see alarms that were closely correlated with each other, as they would have a similar pattern, and we may be able to see where an incident occurs if several alarms come in at once. We can see this if we choose another month. In this month, we can see that these two alarms have almost identical behaviour, as does this one and this one, which also closely matches this alarm up here. As well as looking at the overall top 20, we can look for special types of alarms as well. Firstly, there are fleeting alarms. Fleeting alarms are those that occur once for a very short time, less than a minute, and then do not reoccur within less than 10 minutes. The point about this behaviour is that the operator will not have had time to take action to fix them within a minute, so the alarm is cleared by itself and then does not reoccur. Since he took no action, was it necessary for the operator to know this? Often, when speaking to operators, they will say of this type of alarm, "If that one stays on for more than a minute, then I'll do something about it. Otherwise I ignore it." So why not configure the alarm to behave in a similar way? Most DCSs have delay functions for alarms, so it could be set up to only alarm if it is on continuously for 1 minute. Of course, if this is done, the operator needs to be aware that this is how the alarm works. We have a list of the top 20, a count of how many times it occurred, a measure of what percentage of occurrences were fleeting, in this case it is 95% of the time, and the average time that it was on and then cleared again. Again, we can accumulate these and see what the total effect is on the alarm system. We can also look at stale alarms, also known as standing. These alarms are those that are on continuously for greater than 24 hours. Generally, these occur on equipment that is shut down, and they tend to clutter up the alarm summary, which should normally be clear with only alarms that require addressing being displayed. For these, we display the count and the average number of days that the alarm has stood for, which, for this alarm, it was on continuously once for 8 days. The other type of alarms we can look for are chattering alarms. Chattering alarms are those that come in and out at a very high frequency. Precisely, this is 3 enunciations within a minute. Generally, these occur when a process variable is very close to its alarm setting and there is insufficient deadband or damping. And again, we accumulate them to see the total effect. So, now we know which tags are causing us a problem. What we want to do now is examine each tag, see what its behaviour is, and what we might do to fix it. So, by default, the first tag is chosen, which is 81LAH1113, the worst behaving tag. We'll change that to 81LIC1118, as being a controller, it has more interesting details to look at. First of all, we have a display in green of alarms over time. So we can see that on the 5th of September, this alarm happened 92 times, and that it was really only on this day that the alarm was a problem. In many alarm management systems, this is the extent of the detailed information displayed about a tag without going directly to the sequence of event SOE data. And really, it's not very helpful. But we have more to look at. The barcode is also displayed, so we can see if the alarm stands. There are 2 additional barcodes to show if the alarm is disabled or if its mode is changed to manual, which for this tag has not happened. In orange, we have intervention counts on this tag, so we can see if there is any correlation with the alarms. On a daily basis, there is not really enough resolution to see this clearly, so the next chart shows each hour as a bubble. The vertical line is still a day, but the horizontal line is for each hour of the day. The size of the bubble is indicative of how many alarms or interventions occurred. Again, green is for alarms, orange for interventions. We can see that there is actually very little correlation between alarms and interventions. This can then be summarised by only looking at which hour of the day the alarm occurred. This can help show if there is some kind of routine task that causes this alarm. Perhaps adjustments are made at the start of every shift. We also look to see what else was an alarm when this came on, and this chart shows which alarms were active as this one enunciated. And, as we can see, there really isn't any. This is typical for a bad actor, because it is, after all, broken. We can also look for alarms that enunciated, so they may have cleared, in the 10 minutes before and after this alarm. Again, not unexpectedly, there are no other connected alarms other than itself, because the alarm is probably chattering. More importantly is to look for interventions that happen before or after. Is the operator doing something to cause the alarm, or is he taking an action after it occurs? This is different from the intervention shown above, because they were on this tag specifically, and of course the intervention may be on another tag. For 81 LAHH 1113, we can see interventions on 81 LIC 1118, which is probably related. It has the same system number and a very close sequential number. But the number of interventions is still very low. We can now go to the Analysis tab, where we can extract some specific diagnostic information. There are 3 measurements we can extract from the alarm messages in the database. We can extract the on-to-off time, which is how long the alarm is on for. We can extract the off-to-on time, which is how long the alarm is off for. And the on-to-on time, which is the time between enunciations. So on-to-off is how long the alarm is on for. So to take a specific example, we can see that 8 times, which is the count, this alarm was on for 41 seconds. This chart would show us if an alarm was fleeting, as all the highest counts would be biased to the left-hand side, showing the alarm was only on for a very short time. As it happens, in this case, it is the off-to-on times that are very short, showing that the alarm reoccurs very quickly, which means it is chattering. So, we can see that on 38 occasions, this alarm re-enunciated within 9 seconds. We can accumulate these counts, so we can see for 80%, with the orange line here, is equivalent to about 26 or 27. So, if we delayed this alarm clearing by 27 seconds, it would remove 80% of its occurrences. This is a very simple change that is very easily implemented, and taken over several tags, could make a significant change to the number of alarms generated. Unlike the fleeting example, where the alarm is prevented from occurring, this alarm does happen, and all we've done is stop it telling the operator that it has happened over and over again. The on-to-on time shows time between enunciations, and this tends to be useful on controllers where we can often see cyclic behaviour indicative of tuning issues. We then have a chart of the main KPIs for this specific tag. We can see the chatters, number of days the alarm occurred, how long it stood, etc., etc. But the 2 most important numbers are down here: the recommended off delay and on delay. And as we discovered, 27 seconds off delay is being recommended. We then have some free format text that is stored in the database so that we effectively perform a mini rationalization for each bad actor we examine as we check our bad actor list, either monthly or the period defined in our alarm philosophy. This also helps us see what thoughts we've had if this tag has come up previously. If an alarm response manual, ARM, already exists, then we can use that as the basis to start this off. So in this case we have the cause, which is the failure of the sump pump to start. We have a consequence, which is the inlet valve has tripped shut. There will be a backup of fluid causing high-level alarms upstream in the process. There is a cost, less than 100k. There is an urgency. That is how long it is before we must react to prevent the consequences occurring, which in this case is 10 minutes. And there is an action. Get the outside operator to check the pump and start the standby if appropriate. It is important that we put in the action, because if there is no action for the operator to take, then by definition it is not an alarm. These are the ARM fields. We then have the bad actor resolution field. The alarm tends to chatter after the trip occurs as the level remains at the trip point. Keeping the alarm on for 30 seconds will remove more than 80% of its enunciations. So we can go through all our tags, each of which is likely to have different characteristics in these charts depending on what the tag is doing. This one has an unusual characteristic. In that the charts are showing us that the alarm is on for either 19 seconds or 24 seconds. There is a similar situation for the off to on, and this is quite likely due to a piece of software that is running and periodically re-enunciating what it sees as a problem. Again, we have the KPIs, and we can fill in what we have diagnosed. We'll choose another tag. What we can see here is a tag that both fleets. It is on for a very short time. Nearly every time it happened it cleared within a second, and it is also chattering. This means that very short delays are all that are required to fix this tag. In summary, intelligent plant's alarm analysis can indicate if there is an alarm management problem, where that problem lies, and crucially, advice on how to rectify the bad actors. So, this completes our overview. Thank you for your time. I trust you found it interesting and informative. For further information, contact Intelligent Plant. Thank you.